In this video, I will explore how the Manim handles the creation of such graphs and their transformation from one graph to another one, setting different attributes to each graph. The way we used to create this rows pattern is longer than necessary, but it was important to understand the mechanism of Manim, basically how Manim renders the objects in the scene. To simplify our code, we will be using Parametric Curve, a subclass of the VM object, which is very convenient in such scenarios. The functionality of the Parametric Curve is exactly the same as how we created the rows pattern. This was the code to create the rows pattern. And by using Parametric Curve as a parent class, it simplifies the code significantly. Basically, there are two main arguments in this class, the function and its range. If I compare both the blocks of the code, you can see that the highlighted lines in each block are exactly the same. Notice how effortlessly we can create the same effect with the help of Parametric Curve. Let's try to understand its working by displaying a simple curve, sine curve for example. So, first as usual, I define a variable sine curve and instantiate it with the class Parametric Curve and specify the function with its range as arguments. You see, from lines 4 to 8, the function returns an array of 3 elements. These 3 elements are the x, y, and z coordinates respectively at a particular t value. I'll just demonstrate what I meant by that. Assume that the range is from -5 to 5, with a step size of 2 units. This means that t increments by 2 units at a time. The function that we defined in the creation of sine curve, it returns an array of 3 elements, x, y, and z, at each value that t takes while going from -5 to +5, which means at t equals -5, x is also -5, and y takes the value of sine t, which is 0.96. In the same way, at t equals -3, x is -3, and y is -0.14, and so on. Z would be 0 throughout the journey. However, as you can see, this curve can't be quite identified as a sine curve. Due to the larger step size, there is no smoothness. To make the curve smoother, I need to reduce the step size. But by doing so, the computation power increases, as d would take more number of steps to progress. You see, the computation power increases as I lower the step size, but so does the smoothness. Therefore, we need to find a balance point where the curve appears smooth enough while maintaining a reasonable computational efficiency. The main advantage of using the parametric curve is, of course, the easiness, and also we can list the discontinuities in the function in the curve. Take the step function for instance. If I do not pass the discontinuity as an argument, I get this weird looking curve. Now observe the change, the visual precision, just as I pass the discontinuity. Another parameter of this class is tolerance of the discontinuity, which is required to specify the boundaries. Its default value is 10 raised to the power -8, which is very close to 0, but not 0. It is necessary to prevent any potential rendering artifacts when evaluating the curve at the boundaries. And just for fun, if I pass epsilon to be 0, observe what does Manim think of our curve. So, the use of epsilon is essential for the practical purposes. Now, I'm going to further simplify the things. Manim has this function graph class, subclass of parametric curve, with the default range spanning the whole scene from -8 to +8. With this function graph, our task becomes slightly easier as we need to pass the expression of the function only rather than an array of points like we did in the parametric curve. Speaking of graphs, we are quite familiar about the coordinate system. Let's try to understand its representation in Manim so that we can picture the same graph or in fact any graph in a proper manner. So first things first, the way I created these horizontal and vertical axes is by using the axis class. It's a subclass of two major classes, the coordinate system and VGroup. The first one is the coordinate system, which is an abstract class. This simply means that it doesn't have the complete implementations of the methods it provides. It just acts as a base class for all its subclasses. For instance, coordinate system has two subclasses, the axis and the number plane. Once we understand how axis works, it would be much easier to deal with the number plane later. The second parent of axis class is the VGroup. Earlier, I slightly mentioned VGroup in the code. I guess we need to take a small detour to understand how VGroup works. I hope you remember what an M object is, how is it defined, and the role of the points with their location in canvas. The points give an M object its shape, its face value in the canvas. Whether it's a circle, a square, a hexagon, a star, or any other figure, Manim renders these figures based on the points defined on the canvas. Now imagine, if I want these figures to have the same width, color, opacity, or maybe the scale size, setting these attributes separately for each figure would be very tedious. Can you imagine how many lines of code it would take if there were 100 shapes or even 1000 shapes? To prevent this cumbersome way of dealing objects, let's define a variable shapes and instantiate it to VM object. And all of these shapes are being added to this variable. This way setting the attributes becomes much easier. I mean, I can set the width or the height. I can even scale them or set the color with just one line of code. But then another problem arises. The problem is that every object is now located at the same point. It looks like they are stacked on the top of each other. To arrange them properly, I can use the arrange method and specify the direction of the arrangement. For horizontal arrangement, the direction would be either right or left. And through the birth parameter, you can set the spacing between any two neighboring shapes. In the case of a vertical arrangement, I specify the direction as up or down. If the arrangement is along the z-axis, which is into the plane or out of the plane, the direction would be in or out accordingly. And to represent them in a grid, Manim has arrange in grid method. You see how easily we transform the figures, set the same attributes, and arrange them in a particular fashion. This is called the grouping of M objects. And these shapes that we added to the variable shapes, they are called the sub-M objects. This is exactly how the class group or VGroup works. Group is for the grouping of M objects and VGroup is for the grouping of VM objects. We have these horizontal and vertical axes. These are actually called the number line. The number line class has many parameters, but the key ones for displaying a standard number line are these highlighted ones. And to understand each one of them, I will demonstrate the changes you can achieve by passing different arguments. The xRange parameter, it allows you to adjust the range of the number line by specifying the minimum, maximum, and the step size as a tuple or the list. With the width parameter, I can modify how long do I need the number line. The parameter include text toggles on and off the text on the number line. And similarly, include numbers and include tip control the visibility of the numbers and the arrow tip respectively. Now suppose the situation asks to show the decimals on the number line. We can use the decimal number config parameter, and also with the help of this parameter, we can specify the number of decimal places. Imagine another situation which demands to exclude some specific number, like 0.4. In this case, we can use numbers to exclude parameter to exclude the specified number from the number line. Now, before we get back to the access class, I need to mention two important methods of the number line that might be useful in the long run. Notice that the numbers on this line do not actually map to the location coordinates of the point as x, y, z on the canvas. For instance, this dot can be at any location on the number line. So to know the location or the coordinates of the number -6 in the scene, we need to call number to point method, or N2P for short. It returns an array of 3 elements specifying the x, y, and z coordinate of the canvas. Conversely, if you need to find out what number is being displayed at some coordinate x, y, z, we can use the method point2number, or P2N for short. Now, enough we know about the number line. We have everything to understand the creation of access. So let's finally just head back to the access class to draw some graphs. We are already familiar with this horizontal number line, which is the x-axis, and the vertical one is the y-axis. To modify these axes in the canvas, we have these parameters. The x-range parameter specifies the minimum and maximum value of the x-axis. The default range is -8 to 8, with a step size of 1 unit. The same behavior applies to the y-range parameter for the y-axis, but the default range here is -4 to +4. To adjust the dimensions of the axis, like the height and the width, we can use the respective parameters. To make some modifications in the axis, such as the tip, the text, we can do so by using these 3 parameters. If the modification is same for both of the axes, axis config is the parameter to go. In case the modification is specific to only one of the axes, the same modification needs to pass only to that respective config. There is one more way to display the numbers on the axis is by calling addCoordinateLabels method. Moving on, the next step is to label the axis. By calling getAccessLabels method, in the case if no arguments are passed, the default labels x and y will get displayed. Axis has a method getGraph, which returns the parametric curve, which is useful for displaying any type of graph. To display a sine graph, for example, I need to pass the function in the getGraph method along with the range of the function. If the range isn't specified in the method, then the Manim implicitly takes the whole x-axis as a function's range. Similarly, I can use a NumPy's cos function directly to display the cosine curve. Another important thing that I want to stress about is how to access the location of any coordinate point x, y. Just like with the number line, in access class as well, the coordinate points of access do not necessarily map to the location coordinates on the canvas. For instance, the location of this dot, the axis coordinates are -4, 1, which is different from the canvas's location coordinates. To access the location coordinates, I will use coordinate-to-point method, or C2P for short, then specify the arguments x and y coordinates of the point. Conversely, to find out the axis coordinates at any location of the canvas, I would use P2C method, short for point to coordinate. In addition to this, to display the horizontal dashed line which stretches from the y-axis to this yellow dot, we can use getHline method, specifying the coordinates of the yellow dot here as an argument. In the case of a vertical line, the method changes to getVline. And of course, to change the thickness or the color of the line, we can pass those arguments as well. Now, it is time to put everything we have learned so far into a practical illustration. Suppose a car starts moving on the x-axis at t = 0 with an uniform acceleration of 2 meters per second square. The condition is it accelerates only for first 3 seconds, and after that it runs with a uniform speed for 2 more seconds. Now we want to display the distance versus time graph, that is the distance x as a function of time. To plot such graph, we need the equation x of t. The kinematic equation in this case would be x equals ut plus half at square. Here, the car's initial speed u is 0 and the acceleration a equals to 2 meter per second square. So x of t becomes t square until t equals 3 seconds, and after t equals 3 seconds, the car maintains a constant speed of 6 meter per second, hence x of t becomes 16 minus 9. Moreover, the speed varies as acceleration times t for first 3 seconds, and then afterwards, the speed becomes 6 meter per second. Now, before I code or I define the axis in the code, I need to ensure that both of my axes fit within the canvas's frame. I know that at t equals 5 seconds, distance would be 21 meters. So I need to set the y range to be at least 21 units and x range to be 5 units at least. Additionally, we know that the frame height is 8 units, which means the maximum height of the y-axis should be less than 8 units to ensure it fits on the screen. Notice that if I set the step size of 1 unit for both of the axes, the y-axis becomes too cluttered with the numbers, which makes it difficult to read. To improve the readability, I will increase the step size to 3 units. The code until now is similar to what we previously did for the sine curve. Moving ahead, to display the distance time graph, I'm calling axis.getGraph function with the arguments goes as lambda t square if t is less than 3, else 60 minus 9, and setting the range of this graph to 0 to 5. The return value of this lambda function in line 14 is like a ternary operator. If the value of t is less than 3 units, the function returns t square, otherwise it returns 16 minus 9. If I want to display a tangent at any x coordinate, well, in this case the time coordinate, axis class has getTangentLine method where I need to specify the time coordinate and the corresponding graph as arguments. Let's say at t equals 2.5 seconds, I want to display my tangent. The tangent line would look something like this. Now, if I sweep the tangent line from t equals to 0 to t equals to 5 seconds, observe how the slope of the tangent changes. To make it more visually clear, I'm going to add a dot whose y-coordinate equals the slope of the tangent. You will notice that after 3 seconds, the slope becomes constant, which is why the dot starts moving horizontally. To make it more vivid, the red curve here is a speed time graph. And observe the dot's motion. It moves exactly on the red curve, which implies that the speed of the car is a rate of change of distance. To avoid the confusion about which curve represents which graph, I will label them x of t and v of t. Let's implement all of this in code. The lines from 22 to 26 is our usual getGraph function, where I'm passing the speed equation. And the lines 28 and 29, they show how I create the labels using getGraphLabel method. The first argument in this method is the graph itself. And the second argument is the label text. To get the slope of the tangent, axis has this method, slope of tangent. But it is not quite accurate in the cases where both of the axes have different step sizes, which happens to be our case. Take this line of code as a reference. It gives the slope 1.19 at t equals 2.5 seconds As we know, the speed at t equals to 2.5 seconds is 5 meter per second. So the slope at this time should be 5 units. Well, this discrepancy is not exactly a bug, as this value of slope 1.19 is used to render the tangent line perfectly in the visual context. To circumvent this, we can find the slope using the first principles of calculus, with the epsilon in the code set to 10 raised to the power minus 8. Additionally, to find the area under any curve, we have get area under graph method, and the arguments in this method would be the graph and the range of the area. And just like with the above methods, with this method too, I can change different attributes of the shaded area, like its color, its opacity, by passing the respective arguments. Well, that's all for this video. I know I have so much to talk about Manim, the other features of Manim like image and object, SVG object, and of course the 3D figures. So until the next video, try experimenting with these methods to create some interesting curves. Try to modify some attributes to add your own creative touch. I'd like to take a moment to thank you for watching this video. I hope you learned something unique today, something new maybe. And if you did, do not forget to hit that like button. And I'll see you in the next video.